Morning. Ah, hier hast du Batterien rein. Good morning. Can you hear me? Ja. Machst du mal da?
Ja.
Das, was jeder Deutsche mal gemacht haben muss, ne? Einmal die Ostküste runter.
Ja, ich war glaube ich, auf Neuseeland und habe da Freunde besucht.
Ja, cool.
Ich glaube, 10 Tage waren wir in Schwaben.
Eben das Ding an. Wie geht der an? Ja, das ist cool.
Das war so das Klassiker machen, habe ich.
Starten wir aber drüben an dem Welcome-Ding. Ja, genau, da haben wir auch viele Abiturienten getroffen. Viele Eltern auf Elternzeit. Ich hatte da 3 Monate. Also 2 Monate aus 3 in einem Monat oder knappe 2 aus 3. Nee, das haben wir noch von hier aus gemacht, da hatte ich Sabbatical mal. Ja, von China aus ist es auch relativ weit. Wieder auf dem Kopf. Can you guys hear us? Das Ding an hier? Ah, du bist hier gemutet. Hello, hello. Can the studio hear us? Checken wir doch mal, aber ja, müsste. We are already being recorded.
Test. Okay.
We have audio with the AirPods, but not with the camera.
put him on the screen. Wow. All right, I see the screen. Hello, everybody. Hello, Germany.
Hi, Marcus.
All right. Okay. Hi, everybody. We have the live demonstration for TRUMPF additive manufacturing with our colleagues in Germany. I welcome Severin Lucius, our application lab in Stuttgart, in Germany, and he will guide us around through his lab and share some information about additive manufacturing of metal parts. Hi, good morning, Severin.
Good morning, Marcus. How are you?
I'm fine. Yeah, just rushed over to the booth. I was in a customer discussion, but it's all fine now.
Very good. All right, welcome to our showroom here in Ditzingen near Stuttgart in Germany. This is the TRUMPF headquarters, and it's also the headquarters for our additive manufacturing business. My name is Severin Lucius. I'm responsible for applications here, and I would like to take you on a tour through our showroom, show you the machines and the applications that we have.
All right.
So, Marcus, I guess we're starting with a quick introduction of the process itself. TRUMPF is offering metal 3D printing machines. That means we can 3D print parts from metal powder, and the process has been invented at the end of the 1990s by TRUMPF and the Fraunhofer Institute. The technology is quite simple. You're applying a thin layer of metal powder onto a metal plate. You use the laser beam to melt this powder to the plate and move the plate down a little bit, apply the next layer of coating, and the same process repeats over and over. Lasers weld the powder to the underlying structure that has already been built. And that's the way our parts grow over time to build up metal parts with a very high density and mechanical properties that are about the same as a cast part.
All right, we have also some parts here on the show. If you're interested how the parts look like, we can just
I think
go to the left here and see some parts.
A very good first look is actually our TV tower here. I really like to show this TV tower because it shows the possibility of 3D printing very well. First of all, these are all metal parts, obviously. Most of them are printed in aluminum. And starting from the bottom, maybe we can take a closer look at these parts here. You can see that we have manifold structures here that are, of course, possible to print with bending tubes here. That would be very difficult to produce in a mechanical way by abrasion. Then we have cooling structures here with these very filigree structures and cooling channels inside. We can, of course, print these bionic shapes that remind of bone structures that have a very high strength and support the weight here of the complete tower. We can integrate functions, like we can use the elasticity of the material here, for example, for these connectors, where the part on top just snaps in place and can be released by just pushing these clamps here. We can also use the elasticity of the material to really have a spring-loaded part here. This is calculated in the software, calculating the material properties of this part to then design it in a way that it is movable. And we can print also functions like this. This element here is turnable. It's difficult to see on the camera, but there are gears inside that then turn a shaft in the center that will rotate our antenna on top. Now for this tower, obviously, this is just a show. So we are just showing what's possible, but all of these material properties, these parts that we built here, these functions can be used in real parts, and I'd like to show you this later. Then, of course, the top section here of the TV tower shows the different materials that we can use. In general, you can print every material that you can weld. So most metals, And it starts with tool steel here, titanium, stainless steel, Inconel, so nickel-based alloys, and aluminum at the top. But we can also print copper with a green wavelength machine. So there are really no limits considering the choice of materials and especially the shape of the parts, which is, I think, what makes 3D printing so attractive.
Severin, this tower looks pretty big. How tall is it?
From the bottom, I'm rather small. I'm just 1.70 m, but this should be about 2.30 m, I think, okay, including the antenna.
Wow.
Yeah, Nico is moving out a little bit
okay,
to show the dimensions here. So, yeah.
Fantastic. Yeah. And it's all designed for additive manufacturing, right? It's all
exactly, yeah. Of course, there's special software that you can use to optimize the shape of the parts to fulfill a certain function. We can calculate with material properties in mind and the ideal shape of the parts. And that's exactly what's so nice about 3D printing, is that you are very flexible in shape, and you can build the ideal shape of the part and really only use the material that you need for the functionality of the part.
That means you can reduce the numbers of parts, avoid assemblies, for example. You can integrate.
Yeah, right. Yeah, for assemblies. So when you want to optimize for 3D printing, if you really want to get the most out of the technology, there's usually 3 things that we look for in a part. First of all, we look at the performance of the part. Is there a way that we can increase the performance of the part? So can we, for example, make the part lighter? Can we make the part stronger? Can we increase the performance of the cooling function that the part has? That's the second point already here, is functional integration. Are there any functions of the part, or of course of a complete assembly, that we can integrate in one 3D printed part? And often we can replace one assembly of multiple parts with just one 3D printed part. And then the third thing that we look for is, of course, flexibility. For a lot of applications, it is necessary to have flexibility in the shape. So every part could be individual, but also if you look at prototyping, where you want to increase the development cycles of your, let's say, machine development, in the example of TRUMPF, we want to be more agile in our development, then 3D printing is a good way to increase your development cycles, be faster with prototyping, and through this, be faster in your development of new machines. And we use this technology at TRUMPF on the one hand for prototyping, but we also have serial parts here at TRUMPF already that are 3D printed, that we built on our TruePrint systems for other TRUMPF machines, for example, for the cutting machines.
I see the TruePrint 1000 in your back. Maybe we jump into the machines, what we offer, and explain the differences, different sizes and the different functions, what we offer with that, to show the key knowledge of TRUMPF in that process. Right.
So I'll just walk you through the machines, and we'll start with the smallest one, the TruePrint 1000. It's our first and smallest machine that we introduced when TRUMPF got back into 3D printing. I mentioned earlier that we were pioneers of metal 3D printing at the end of the 90s. TRUMPF paused these activities while 3D printing of metals was still mostly in R&D. And we got back into 3D printing about 8 years ago with this machine. And this is a fairly compact machine, easy to handle. And the main difference between this machine and all the other machines is the build envelope. So the maximum size of parts that we can build. And for the TruePrint 1000, you can take a look here at these sizes. For the TruePrint 1000, we're talking about a 100 millimeter diameter here and a 100 millimeter height. This is the size of parts that you can print. The larger machine, TruePrint 2000, goes to 200 round and 200 high. and then TruePrint 3000 and 5000, we're talking 300 millimeter diameter and 400 millimeter height. So you can already print fairly large parts in these larger machines. But let's get back to the TruePrint 1000. You can see the machine has a cylinder printable. We can look into the machine. You can see these round cylinders. Here in the center is the build plate. You can see the machine has not been started yet. It's just prepared to be started now. We have the build plate in the center. On the left, the lighter circle here. This is the powder that is supplied to the process. And then powder that is, we always use a little bit more powder, and the powder that's not used for the layer is then moved to the right here, which is the overflow, where unused powder is then recycled. But with this machine, we have some nice features. For example, here in the center, we can load multiple of build plates. So we can have multiple substrate plates stacked on top of each other. And then when the first job is finished, the build plate is moved to the side by the coder that you can see here on the left. That's the knife basically that applies the powder. The finished build plate moves to the right. A second build plate is hidden underneath so that you can continue producing on the machine up to 4 jobs in a row before you need to unload the finished jobs and you load fresh powder. So that's the TruePrint 1000. A typical application for the TruePrint 1000 is in the dental industry. So for example, we have crowns and bridges that you, I think, also have at the show. Let me open this here so I can show you the part. So you want to film it here on the table? Yeah.
We have a similar part here on the booth.
Probably easiest to film here on the table. Perfect. So you can look at the actual part. And what you see here is exactly what I mentioned earlier. These are more than 100 individual parts that are automatically placed here on the substrate plate by software. So the complete production chain of these dental parts is digital. The dentist scans your inside the mouth, creates a digital model of your tooth. Then they model this crown on top of it. The digital model is sent to the company producing these crowns and is automatically placed on the build plate, supported with these fine support structures here at the bottom, and produced. Such a dental job here, which is, as you can see, not very high, runs for about 2 hours on a TruePrint 1000. And as I mentioned earlier, if you want to have the machine running overnight, this job will be moved to the side, and a second job can be
so that means your
started automatically up to 4 times, so that you can have
so your machine is running 8 hours with 4 jobs automatically without any manual interaction overnight.
Exactly. If you have 2 hours per job, you can run up to 4 jobs. It's actually a little bit more than 8 hours that the machine can run. So you can imagine that you don't need a night shift anymore. Machine runs through the night. In the morning, you have four jobs ready. You take them out and can load new powder, new substrate plates, start the machine again. So this is really great for companies that have higher labor costs, like we have here in Germany, where you do not want to have a night shift operating the machine. And that, of course, brings down part costs. Build time and the uptime of the machine, the use of the machine, of course, are very important to bring down the part cost. So with the TruePrint 1000, we have the most attractive part cost in the market, which makes 3D printing and the TruePrint 1000 really the state of the art for printing of those dental crowns and bridges. Wow. But we can take it even further. If you look at the TruePrint 2000, we have a 200 millimeter round build plate. And the great thing about the TruePrint 2000 is that it has the same fine 55 micrometer spot size that we have in the TruePrint 1000. And with this this 55 micron height of the build chamber, so that means the gas flux in the chamber is very consistent, so that you have no disturbance of the laser beam by fumes or spatter. We can achieve a very high quality. And if you look at these parts here, these are RPDs, removable partial dentures. So that's your tooth placement that you can still need to be cheaper than implants or crowns and bridges. We are talking about $10 per part here that we can achieve with the TruePrint 2000, and you can see this very high surface quality. And thanks to the high quality of the machine, we can even build them upright, have more of those RPTs on the build plate, which brings down part costs further below the $10 mark.
Severin, you said $10. Is that for
the machine
part,
is just as popular?
What kind of material do you use?
These here. So in the dental industry, cobalt chromium, special alloy is most popular. So the crowns and bridges are cobalt chromium. The RPDs are mostly cobalt chromium. There are some companies moving to titanium now. Titanium is more popular in the medical industry. So the parts that you see here are spinal cages. That is an implant for the spine, and you can see this. This is a titanium part. It has this lattice structure here, and these parts will be filled with I don't know the English word, basically bone structure, and be implanted into the spine to grow basically into your spine and stabilize it. These parts are, as you can see, all the same. These are standard parts that are produced on the TruePrint 2000 from titanium.
Isn't it difficult to handle titanium powder?
Titanium powder is actually not the most difficult powder we have. Obviously, when we work with these metal powders, we try to avoid humidity in the powder. And for titanium, you should avoid to use nitrogen when having the machine running. So the machines are always flooded with inert gas while welding. Everyone who's welded knows that very well, that you need some shielding gas. For our process, the complete machine is completely flooded with gas. And we usually use nitrogen, but for titanium, we use argon to process the titanium. Other than that, titanium is not much more difficult than other metal powders. We can handle it in a very similar way. Obviously, then when the machine is finished, we can take out the finished part, and we have a lot of powder, unused powder in the machine as well, that we want to recycle. So it is important to if you want to maintain a high powder quality, to not contaminate the powder with anything, to not get humidity into your powder, but also we try to avoid contact to oxygen. For titanium, it wouldn't be that bad. Titanium is a very stable material, let's say. But nevertheless, from TruePrint 2000 on, all the large machines, you can unpack inside the machine. So there is a powder conveyor integrated into the machine here in the TruePrint 2000 and 3000, so that we can directly feed the unused powder into a sieve or into the overflow bin of the machine, where it is still in an inert atmosphere, so it doesn't have contact to the outside air and is not contaminated. And we can keep this powder cycle completely inert, so powder never sees air and stays fresh.
So that means you move out the build cylinder and the powder supply cylinder out of the machine and bring it to a separate station, right?
Yeah, that is possible from TruePrint 2000 on, but actually for the smaller machines, we prefer to unpack in the machine. If you have a smaller job, there is really, it is often faster and easier to unpack in the machine. Of course, when we're talking about the larger machines, like the TruePrint 3000 that you can see has just arrived yesterday. We have a brand new machine here in the showroom. It's not operating yet. In the TruePrint 3000, we have these large build cylinders that we can also see in the TruePrint 5000. And those cylinders, these large jobs, are very difficult to unpack in the machine. So we prefer to do it outside of the machine. And that, of course, also helps to avoid downtime. So if you look into the TruePrint 5000, I can open up the compartment here at the bottom, move the panel to the side. So in the TruePrint 5000, we have these large build cylinders. And unfortunately, there's a filter in the way here, so I cannot open the door all the way. But there is a second powder supply cylinder in here. You can see this is the same size as the build cylinder here on the left. And these jobs, there's a lot of powder inside. There are huge parts inside. They are heavy. You cannot lift them out the top. So our concept here is to have these powder supply cylinders and build cylinders taken out at the bottom. So this machine, the TruePrint 5000, can be automated. There's a great video by BMW just released that you might want to have a look at, who are really automating the complete TruePrint 5000. So this machine, these large jobs, they can run more than a week unattended. And when it's finished, could be in the middle of the night, you never know. The machine doors open automatically. An automated forklift can drive in here. Cylinders are unclamped automatically. You can take the cylinder out, take the empty powder cylinders out, feed it with new fresh powder, put an empty build cylinder in, doors are closing automatically, and the machine starts itself. So this machine can run almost completely autonomous. And while the machine is building the next job, you can take care of these cylinders. You can fill in new powder into the powder cylinders, and you can unpack the build job in an unpacking machine. So in our case, we have this unpacking station here, for example. This is a version where you feed the cylinder at the bottom. So we can put the cylinder in here at the bottom. Then part is pushed up, and here with these gloves, I can then basically take out the powder with this powder conveyor here inside. You basically, it's just a vacuum cleaner if you want. Remove the powder that is not used. The powder is then conveyed here into a filter, a sieve. And this sieve here then sieves out large parts, for example, remains of the support structure, maybe larger spatter. This is then trash, but the other powder can be reused and be sieved directly into the build cylinder again, and those build cylinders will be fed into the machine again, ready for the next job.
Severin, you just said the machine at BMW is fully automated, can change the cylinders at night without any manual interaction. Is that a vision or is it reality already?
Well, it is a reality at BMW, but I think we have to be, we have to look at the applications that we have for 3D printing at the moment. 3D printing is coming from the research labs. At the beginning of the 2000s, first machines were installed in research labs. Some production facilities, of course, already. Markus, of course, has been part of this journey at TRUMPF. You have been part of this journey yourself. And one of your very first customers back then is replacing their Truma form, so the old TRUMPF machine, with a TruePrint 5000 now. The Truma form machine has been running for 20 years in production at this customer, and is being replaced now with a TruePrint 5000. So there was production, but really the majority of the machines were running in R&D, were running in prototyping. So the steps from prototyping, from R&D, small numbers of parts, really to serial parts, is only happening now. And we see it happening in aerospace, where of course part cost is less of a concern, but we are also seeing it in our own company now at TRUMPF. So if you look at one part here, for example, this is a build job that we showed at Formnext last year. And it's a part that is actually used in our own 2D laser cutting machines. You can see 380 parts in this TruePrint 3000 build shop, stacked on top of each other. And each of those parts, let's have a look here. These are small motor coolers that cool an electric motor in our focusing unit. And of course, what's important about this part is that it has a good cooling function and that it stays on top of this motor safely, because the focusing units move very fast in our machines. And the old part is this brackets with stainless steel inserts. We need stainless steel for our cooling water. We cannot have our cooling water in contact with aluminum. So we needed this to be stainless steel, but we needed the aluminum for the heat conduction here so that we can cool the electric motor, that this is clamped on effectively. So then we have these 3 screws that need to be tightened at exactly the right momentum so that we enclose the motor safely and the cooler doesn't fall off in operation. And when we redesigned this part for additive, we came up with this part. You can see we have the cooling here on the surface, so we can improve the cooling function of this part by having a very cooling, that is the cooling water actually cool the actual outside of the part and not rely on heat conduction as with the conventionally manufactured part. And the neat thing about this part is, if you look very closely, you can see the wall thickness change here. And we were able in the design software here to calculate the elasticity of the part and integrate a spring function. So this here is flexible, and in assembly, we can just use a screwdriver to open this up, insert it on top of the motor, release, and it automatically clamps in place with the force that we need so that it is safely mounted on this electric motor. So this not only saves cost in production of this part. I don't know if our purchasing did a very good job about it, but we bought this old part here for 150 euros, and we're able to produce this part for 90 euros at the moment. And we have produced it for the last 3 years already. So this is one of our first serial parts at TRUMPF that we produced on an old generation TruePrint 3000. 90 euros is already much better than 150, but we also save effort in assembly of this part because we don't need to assemble these 10 parts anymore. We don't need to attach it to the motor with momentum. Instead, we just slide it on and it stays in place automatically. But the good thing is, if we would now take this part from an old TruePrint 3000 onto a new TruePrint 3000 and ramp up the number of parts that we produce, and we can really fill the complete build envelope of a TruePrint 3000 and run this machine at maximum efficiency, we can get the part cost down to 30 euros. And 30 euros compared to 150 euros is really mind-boggling if you still think about 3D printing as an expensive technology. You couldn't produce this part in any other way. And in fact, you can't even produce the conventionally manufactured part at this cost. So you can see that with the new generation of 3D printing machines, we're actually moving into a territory where we can replace fairly boring conventional parts. And we're not talking about fancy aerospace parts anymore. We're talking about our very own parts here in our laser cutting machine.
Severin, I have two questions about this build shop. The first question is, how long does it run on the machine? So what is the actual time what you need at the moment for this build shop here? Just that we have an idea how long this machine is running.
Yeah,
any manual support.
So yeah, that's this job should probably run for about 4 to 5 days. I don't have the actual number, so it should be about 4 days here.
Okay, 4 times
for this
24
job,
hours,
it's
right?
the duration of the job. Of course, yeah, uninterrupted production. Before then, of course, we take out the cylinders, we feed new powder cylinders and start the machine again. So this takes about, say, an experienced operator can reload the machine in about an hour or two before it's ready to produce the next job.
Okay. And my second question is, we did this design change internally with your experience and your team experience. How about our customers? Can we help them to optimize the design for additive manufacturing as well?
Yes, of course, yeah. So these three things that I mentioned in the very beginning, performance, flexibility, and functional integration, that's really what we also train our customers to look for in their own company, in their own production. And there are trainings available to learn about this, but we also have consulting, and we also have our sales team has access to all our help our sales find this kind of applications at our customers. And when customers need more support with optimizing their production, we can of course do this remotely.
That's a very interesting.
Australia is far away from Germany. I think, as you can see here, remote support works pretty well.
Perfect. All right, good. I think we're almost at the end. Severin, I look around. Are there any additional questions? One second, Severin. Here's a question: if we can build up 3 parts with zinc. Have you ever done this? Yeah.
Yes, there is a pure zinc part. Let me think. Do we have pure zinc? I don't see why it shouldn't be possible. Zinc is weldable as a pure material. So I do not know if we have pure zinc powder available at the moment. But as you know, the machines are open systems. So in principle, every material that can be welded and is available in powder form can be used in our machines. And we're happy to try this out. If you want to see what the machines can do on pure zinc, we need to find someone to supply the powder, and then we can develop the parameter here, or help our customers develop the parameters themselves.
I think that's a good hint. The TRUMPF machine is open for any powder. We can help you with some standards, but if you have a special request, we can help you with basic understanding of the process. But at the end, you can run any metal powder in that machine, and you find the process for your specific material.
Exactly.
Okay, there's one more question about process control.
Good one. Yeah, process control and regulation. That's 2 very interesting topics. We have in the larger machines, TruePrint 2000 and up, we have a high-end melt pool monitoring system that actually looks through the laser beam into the melt pool and measures the temperature of the melt pool through the emissions of the melt. And this melt pool monitoring system will give you a 3D map of your built part, showing 3-dimensionally the temperature that was achieved in the melt pool. So
the line is interrupting, Severin.
So that you can identify to check the quality. Sorry. Can you hear me again now?
Yes, now it's okay.
Okay, sorry, yeah. Seemed to be a bad connection. So we have melt pool monitoring that measures the temperature of the melt pool throughout the complete build job. And you can look at it while the machine is running or when the machine is finished. You can look at the job and see the temperature of the melt pool everywhere in your part. And through this, identify potential defects in the part. Where there could be something wrong, and compare with a reference build job. So if you can tell the machine this reference build job was good, so the machine will compare every job to this reference job and alert you in case of any deviation from this reference job. Another monitoring solution we have in the machines is powder bed monitoring. So there are multiple cameras in the system looking at the build plate and looking at the surface of the part before and after coating the next layer of powder to identify if any of the parts are deformed, to react to that more powder and filling a potential void. But also for this, the operator can be alerted to take a look at the machine and act if necessary.
Okay, thanks, Severin. I look around if some other questions. If not, then thank you to Germany. Yeah. Enjoy your breakfast now. And I hope to hear you tomorrow again. Yeah, thanks for coming. Thanks for this chance to introduce our technology and our showroom here. And I hope to see you someday in Germany. All right. Thanks, everyone. Bye-bye. Take care. Thank you. Bye. Take care.